Welcome back to OCHEM 1 Weekly Review. This is week 9. We are almost at the end of Unit 2. We just have one more week from today, which means we have today's weekly review and next week's weekly review. Last week we went over E1, E2, and this week we're going over lots of practice problems, including ranking questions and other material. And the next week we'll do the exact same. We'll do a little bit more exam review, just going over everything that we learned over the past couple of weeks. So yeah, if you guys have any questions, please let me know, and so I can help you beforehand. Anyways, let's get into it. Let's get into some practice problems. All right, so we're going to start off with ranking questions, and then we'll get into reactions. So we're going to draw. So this first one is going to be the first one is regarding radical halogenation. Okay, so those are our, and again, we are by 1 equals most stable radical. Okay, so whenever we're dealing with free radical halogenations, or sorry, not free radical halogenation, we're just dealing with radicals. So radicals, there is a trend. So it helps to know that trend. I would suggest writing that trend first thing whenever you get to your exam or quiz. So I'm going to write it off to the side so I don't get mixed up. So we have benzylic, allylic, tertiary, secondary, primary, methyl, and vinylic. Okay? And within benzylic and allylic, I have 3, 2, 1, 3, 2, 1. Okay? All right. So now that we know our trend, the second step is to label our radicals. Okay? So I know this is on a secondary carbon, and because it's on a double bond, it's going to be vinylic, which is very unstable. So this one is on a primary carbon, but it's benzylic because it's 1 carbon away from a benzene ring. This is also 1 carbon away from a benzene ring, but the difference is this is now a secondary carbon. The last two, there's no benzene, so there's no resonance involved. So it looks like this is a secondary carbon and this is a tertiary carbon. Okay, so if you need if you don't know how I got those, positions and benzylic, please go back to a previous weekly review to review that material. So now I'm just going to look at my labels and I'm going to look at my trend, and I don't have to do any work. So I know benzylic is the best one, and within benzylic it goes 3, 2, 1. So this is going to be 1, 2, and then now I have secondary, vinylic, secondary, and tertiary. I already know vinylic is my worst one, so I'm going to put that as number 5. Now between my 3 and 4, I have a tertiary versus a secondary, so it should not be any tricky on that. So it should be pretty straightforward. I know that's rather easy for me, but I hope at this point it's also easy for you guys. Yeah. So next up, so that's number 1. Next up, we're doing carbocation, or you might even see in the question, it might even say ranked by SN1. Okay. And an SN1, as you guys know, has a carbocation intermediate. And so let me draw the structures. So these are a lot bigger than the other ones. Okay, so we're going to have a very similar approach. We're going to remember our trend, we're going to label, and then we're going to rank. Okay? There's really not too much else going on here. Okay? But a couple things. Well, first, I need to draw this properly. Okay, there we go. A couple things is, or one particular thing is, 4 of my structures have chlorine and 1 of them has bromine. Okay, and I already said this is ranking by carbocation / SN1. Okay, so these SN1 my halogens are going to be my leaving groups, and leaving groups have their own priority. Okay, as you go down the periodic table, it increases in priority. Iodine is the best, then bromine, then chlorine, then fluorine. So real quick, iodine, bromine. Okay, and you can ask yourself, why is this the trend? Because iodine contains the largest mass or size, and that large size can hold that negative charge the best compared to fluorine. Okay, so remember, these are leaving groups. When they leave, they have to contain that negative charge. Iodine is the most ideal leaving group because it can stabilize that negative charge the best. Okay. All right, so let's get started on labeling. So this is a primary, secondary, tertiary, this is a secondary, and this is a secondary allylic. Okay, and if you guys remember from my SN1, SN2 chart, there is one of the factors that determines SN1 or SN2, or if it's good or bad, or special points to consider, is resonance. Okay, and if you guys remember, resonance is good for SN1 and SN2. Okay, resonance is bad for nucleophilicity though, because it decreases that negative charges, stabilizes nucleophilicity and nucleophile's reactivity. So if the nucleophile is stabilized, then it's going to be less reactive, which means it's going to be less likely to attack my carbocation to form that substitution. Okay, so that's a little side point. I just want you guys to remember. I'm going to keep saying it as much as possible so you guys understand the science and concepts behind, and not just simply memorizing, resonance bad, 3, 2, 1. Not understand why. Okay. All right, so a couple of things. I have 3 secondaries, but and then a tertiary and a primary, so that should be easy. And I have a secondary allylic. I'm not even going to think. I'm automatically going to put that as number 1, okay? And then after that, I have a primary, so I'm automatically going to be putting that as number 5. Okay. And then I have 3, which is going to be number 2. Now, between my 2 secondaries, you have to consider rearrangement or possibility of rearrangement. Okay, so if chlorine rearranges, it's going to either rearrange to a secondary or a primary. Okay, which doesn't do anything for us. Sorry, I'm looking at the second one right here. So so nothing happens here. Same stability. Okay, but if this rearranges, I can either go to a primary or I can go to a tertiary. See that tertiary carbon right there? It can do a hydride shift, switch with this carbocation, and then the chlorine can come in, or the nucleophile can come in and attack. Okay, so this is a secondary, but it's a secondary that goes to a tertiary through a hydride shifts. Okay, remember SN1 and E1 can rearrange. Okay, always think about that. And for SN2, always think about steric hindrance. Okay, and for E2, what am I going to say? Okay, what's the special thing about E2? You have to have the anti-coplanar hydrogen to your leaving group. Okay, so don't forget these special things whenever you decide or looking at a problem, if you know the mechanism. Okay, so secondary to go to tertiary. So you might think, oh wait, now they're both tertiary, which one's faster, right? So the question really, sometimes it says, rank the fastest SN1 reactions in order or something like that. They use the word fastest, okay? And any shift that takes time and energy, okay? So that is obviously going to be less or slower than something that's already tertiary, okay? So which is why this is going to be number 3, and this is going to be number 4, okay? I really hope you guys are finding it simple and straightforward. Even if the problems get slightly harder or they throw a curveball, the method should be the same, and I hope you guys find my approach helpful and simple to replicate whenever you guys take the exam. Okay, I really want you guys to do well, and I think you guys can do it, or I know you guys can do it. All right. Question 3. Now we're looking at carboanions. Okay, and I'm just going to remind you guys of the trend: benzylic, allylic, methyl, 1, 2, 3. Okay, and within benzylic, allylic, it is 1, 2, 3, 1, 2, 3. Okay. Now for my reactions, they're kind of long, so give me 1 second. Feel free to fast forward if you haven't already. Alrighty. So I have carboanions, which is a negative charge. I have my trend ready. Now what I gotta do is label these. So I have a primary, no resonance, tertiary, benzylic, tertiary, secondary, no resonance, secondary, benzylic. Okay, so this is not SN1 or SN2, so you don't have to worry about any steric hindrance or rearrangement, so don't worry about that. So this is a simple chapter 4 negative charge ranking, okay? Which honestly is similar, or rather it's opposite to carbocation, and carbocation is similar to SN1, okay? Alright, so right off the bat, I'm going to do my benzylic ones, number 1 and 2. So remember, I have tertiary and secondary. So my initial gut reaction is to put tertiary number 1, but remember it's secondary. It goes 1, 2, 3. Okay, I'm glad I caught myself. That would have been embarrassing. Not that it's any wrong to get a question mistaken. Anyways, now I have primary, secondary, tertiary. That should be easy. We already have our trend right there, so I'm going to put primary as number 3, secondary as 4, and tertiary as number 5. And yeah, I believe that should be correct. Okay. If I ever get any of these questions wrong, please feel free to call me out. Send me an angry email. Just be like, hey, you got that question wrong. You're not so smart. Okay. Now I have 2 more ranking questions, and then we'll get into the fun stuff. Well, this is already getting into more fun stuff. Number 4, highest B, D, E. Okay? And like I said, BDE is not the typical BDE that you guys are used to. Okay, BDE stands for bond dissociation, if I know how to spell. Energy. I think that's how you spell it. Give me 1 second. Okay, yeah, I'm not using my mouth. That is how you spell it. Okay, so bond dissociation energy. How much energy it takes to break a bond. Okay, energy and stability have an inverse trend as far as this question goes. Okay, so the more stable a bond is, the less energy it requires to break a bond. The more unstable a bond is, the more energy it takes to break that bond. Okay, and I also mentioned in the previous weekly review that it is a complete opposite trend of radical stability. Okay, and radical stability, so the complete opposite would be vinylic, methyl, 1, 2, 3, allylic, benzylic. Okay, with it being 1, 2, 3, 1, 2, 3. Okay, literally the exact opposite of radical / carbocation stability. Okay, now for our structures, and again, feel free to fast forward or skip ahead. Alrighty. Okay, so what is going on here? We have hydrogens, and that's obviously where we're labeling, okay? But the point is, hydrogens are essentially radicals whenever they leave. I mentioned this in one of the very first lectures or reviews. So this is going to be tertiary, secondary, allylic. This is primary benzoic, and then this is primary. Okay. All right. So I have my trend right there, and I'm going to start ranking. So vinylic, I don't see anything vinylic. Methyl, nothing. I see a primary, which is going to be 1. I see a secondary, which is going to be 2. I see a tertiary, which is going to be 3. Now I have allylic, which is going to be 4, and I have benzoic, which is going to be 5. Okay? That's all there is to it. Okay? Excuse me. Alright. So number 5, we are ranking by nucleophilicity. Okay? So I'm going to scroll down a little bit. Okay. So for nucleophilicity, actually let me draw all the structures. So cue elevator music is the most exciting part. All right. Okay. Just checking if I'm still recording. My mic is not muted. Okay, so we have 5 molecules, and we are ranking by nucleophilicity. Okay, and just like any other problem I've done before, I'm going to give you guys a set of guidelines / trend, so you can just look at it and apply it. Okay. So first thing is having a charge is better than no charge. Okay. Because we want our nucleophiles to be reactive and / unstable, so they can attack and go through with the reaction. Resonance equals bad. Bulky equals bad. Okay? And that's all there is to it. Okay? Really. And obviously, keep the periodic table in mind. We have your bean, which is basicity, electronegativity, acidity, and N for nucleophilicity. So as you go down the periodic table to the left of the periodic table, you are increasing your nucleophile strength. Okay. So first thing I'm going to do is look at all of my structures and see if they have a sodium, potassium, or hydrogen. Okay. Now, if you guys remember from my reviews, if I said that if there's a sodium, a potassium, it is going to be a strong nucleophile because it forms an ionic bond. It's a Gen Chem concept. Ionic bonds, when they dissociate, there is a complete separation of a full negative and a full positive. Okay, so And if they have hydrogens, it is going to be a partial negative charge because hydrogens form a covalent bond with the rest of the structure. Okay, so that is a weak dissociation because it is a weak electrolyte, and when it dissociates, there is a partial negative charge. So out of all of these, I have one that has a hydrogen. Okay, so this is automatically number 5. Okay. I was gonna say something, I forgot. Yeah. Anyways, so next thing we're gonna look at is they all have sodium. They all have a charge. We're gonna see if they have any resonance. Okay. And obviously I have my ester group, which is carbonyl with OR. R is sodium. R leaves, and we have a negative O that obviously can resonate with that. So resonance, is it good or is it bad? Well, it's on the page, so it must be bad. So if you guys notice, we're going in opposite order, okay? I'm going from the worst to the best, okay? Now I have 3 structures left. One with oxygen, one with sulfur, and one with Se, okay, which I think is selenium, not sure. Okay, so that has nothing to do with charge or no charge. That has nothing to do with resonance. Does that have anything to do with bulkiness? If you said yes, you're wrong. Okay, it has nothing to do with bulkiness. Okay, bulkiness, just think about extra carbons. Okay, but it has something to do with our final thing, which is our periodic table. Okay, so if you guys remember your periodic table, it goes oxygen, sulfur, and selenium. Okay, Se. And like I said, as you go down the periodic table, you increase your nucleophile strength. So that's all we need to know to answer this question. This is the best one. This is the second best one. This is in the middle. All right? Easy, right? Fun? Easy and fun? All right. You guys probably hate me. All right. Okay. Let me try to go back. I don't think I can zoom in because these are pretty big as itself. So I'm just gonna scroll through all the ranking problems before I get into the reactions. So there's 1 and 2. There is 3. There is 4. I'm trying to get 2 at a time, but I can't. I don't know what that is. I feel like we can just go away. Or can I delete this? Okay, there we go. Okay, and then there's nucleophilicity. Okay. All right. So let's get into reactions. I'm trying to see if there's anything I need to go over before then. I think I covered everything. I just haven't covered alkene and alkene stability. Not sure if they'll be on your exam, but I think it's important to go over reactions and practice them. Yeah. Okay. So there's not going to be any particular order by this. There's not going to be. It's not going to be like we'll do all lesson 1 reactions, all lesson 2, and then E1, E2. It's not going to go in a nice, neat order like that. Yeah. Okay. So number 1. bromine, we have a methyl. Okay. And I have okay. So here is my approach. So I look at my leaving group. My leaving group is on a secondary. It's adjacent to a tertiary carbon, which is some steric hindrance, but not enough to deter us from doing SN2. So right now it could be still anything. We don't know. Looking at my reagent, I only have a nucleophile, no solvent. That's completely fine. Don't be alarmed if you don't see a solvent. Sometimes it won't be there. Looking at my nucleophile, I have to decide if it's strong or weak. I see my sodium, so I know it's going to be strong nucleophile. So, and I also see my sulfur, which, based on my periodic table, sulfur is a good indicator of the strong nucleophile. Okay, so everything is pointing towards SN2. Okay, so I'm going to follow this reaction through SN2. There's not enough steric hindrance to prevent me from doing so, so I'm going to substitute my S-methyl where my bromine was, and then I'm going to flip the stereochemistry because it is SN2. It has an inversion. Okay. Question number 2. Okay. Okay. So my leaving group is on tertiary, so which means no SN2. So we can cross off SN2 as a possibility. Now I'm left with E2, E1, SN2, SN1. All of them do prefer tertiary, but looking at my reagents, I have a strong base. Okay, NaH is a strong base. This is something you definitely want to remember. This is a very, very strong base. Okay. So obviously we're going to look in terms of E1, E2, and because I said it's a strong base, we're looking at E2. So E2, it will do, elimination. It will form a double bond. We have to look for anticoplanar. However, in the case where we have a line, we can assume that this line is essentially opposite of that bromine. And the reason why I look at that hydrogen and not any of these, okay, so these are my options. I have 3 hydrogens bonded to carbon that's bonded to the carbon that has a leaving. Okay, so when this leaves, it has to form a double bond between one of those bonds. Okay, the hydrogen that's a tertiary, this one will form the most substituted double bond if I do right there, and we do that because this is a small, strong base. Okay, the word small means it's Zaitsev, okay, which means it is most substituted alkene. And strong base means it's E2, okay? And then THF is just a solvent. No need to pay attention to that. There you go. So next, we'll look at something a little bit more challenging. Okay. All right. So what is going on here? Okay. I guarantee you some of you have not seen this yet. I hope most of you have seen this yet, and I hope all of you will know what to do in a case like this. Okay. OH is a bad leaving group. Okay, it's a bad LG. Okay. Halogens are good leaving groups. Okay, so how do we make OH into a good leaving group? Okay, and the reason why halogens are good leaving groups is because they can stabilize that negative charge, while OH is not readily acceptable to accept that negative charge. Water is a good leaving group, but OH is not. Okay, so we have to turn OH into something stable that can leave. This thing is called tosyl. So I think this is how we spell it. Tosyl chloride. Okay? And tosyl chloride is something that attaches on to hydrogen, where the H and the chlorine leave as hydrochloric acid as a byproduct, and tosyl attaches on to oxygen. Okay? So this is your intermediate step. Okay? OTS, oxygen with tosyl group, is a very good leaving group. Okay, tosyl, if you look at the structure of it, hopefully you have seen it in lecture, Google it. Tosyl has lots of resonance stabilizers. Okay, so that OTS can leave because that leaving group is stabilized. We can handle that negative charge. Okay, now we have a good leaving group, and then I look at my reagents. It looks like I have a terp-butyl oxygen with potassium. Okay, I see potassium. That means it has to be SN2 or E2. It's very bulky to be SN2, so it has to be E2. Again, my leaving group's on the line, so I don't really have to worry about anticoplanarness. So um, so it's going to be E2. Is it a weak base, or sorry, is it a small base or a bulky base? And really, I don't have to worry about that because my only option is to put it right here. Because if you notice, putting it right here means that this carbon will have 5 bonds. Okay, C5. Okay, so really, your only option is to put it right here. So at that point, you don't care if it's small or bulky. You're gonna put it there. Okay, but you know, for clarity, this is a bulky base. This is called terbutoxide. Uh, T-butyl oxide, because when the potassium leaves, you have a negative strong O negative charge. Okay, so that strong O negative charge is going to obstruct this hydrogen, and both the leaving group and the hydrogen are going to leave to form this, which is a double bond. Okay. So a couple things that we learned is alcohol is a bad leaving group. Okay. Say that with me. Alcohol is a bad leaving group. Tausyl chloride will stabilize my alcohol and turn it into a good leaving group. Tausyl chloride turns OH into OTS, which is a good leaving group. Okay? And you might be wondering, what about this terbumethyl, or this solvent? This is just a solvent. That's it. That's all it is. It's a polar product, which favors SN1 E1, but that doesn't outweigh the strong base. Okay. So that was very unique. Next up is also something very unique. That's it. Okay. So this is called a, or before I say the name, I'll say the name of the problem at the very end. Okay. So I want you guys to think about this problem for 1 second. Okay. So let's look at everything that's going on here. I have my leaving group. My leaving group's on primary. Okay, that means maybe SN2. Okay, I need a strong nucleophile. Looking at my reagent, I have a strong base, not a nucleophile. Okay, and then you have the other point of this alcohol. What is that alcohol doing? Is that leaving? Sorry if I'm talking a little bit fast. That's probably why I'm running out of breath. Anyways, we learned previously that NaH is a very, very strong base. Okay, so this is a strong base. Okay, so strong that it abstracts this H. Okay, so it leaves us H2 gas, and we get a O negative. Okay. So if this is not our nucleophile, this is a base, its sole purpose is to make alcohol into a good, not leaving group, because we already have a leaving group. It's going to make it into a good nucleophile. Okay? Okay. Let's think about what just happened. Earlier, we learned how to make alcohol into a good leaving group by using tausyl chloride. Now we just learned how we can make alcohol into a good nucleophile. Okay? So alcohol is very diverse, and it could do either or depending on what is being reacted with. Okay? So the H's leave as H2 gas, Na and bromine leave as sodium bromide, and we have a positive charge here, and we have our negative charge on the oxygen. So it's going to attack at this carbon. Okay. Now, yeah, so the same structure is attacking itself. Okay. So the word or the name of that is called intramolecular reaction. Okay. So your answer, and before you get to your answer, whenever you're attacking yourself, you're going to form some kind of ring. Okay. Yeah, 1, 2, 3, 4 carbons in your ring. Sorry, 5 carbons in your ring with oxygen also in the ring. Okay, so I'm going to draw oxygen, and 5 carbons means, so 5 plus 1 equals 6. I'm going to have a 6 atom ring, which obviously represents like a hexagon. So I'm going to draw my 5 carbons. So I have 1, 2, 3, 4, 5. Okay. And yeah, there you go. That is your final answer. See, this is what I mean by fun, because you get to do a lot of creative problems like this. When you get to synthesis, if there already isn't synthesis on this exam, you'll understand the the, the how complicated and different it can be. And I love synthesis questions. I think it's the best part of OChem, or one of the best parts, because you can get very creative with it. But yeah, there you go. Okay. All right, let's see. So let's see if I can find some really cool questions. Oh, so real quick, I'll do some Chair, Newman, and Fischer flips. When I mean flip, I mean if it's SN2, you got to flip it, right? You got to flip the stereochemistry. So how do you do that? It's actually it's more straightforward than you think. SN2, Newman, Fischer, and Chair have easy stereochemistry like identification, like if it's on the left side versus if it's pointing up or equatorial. So you're able to see that. Okay, so I'll give an example. So let's start off with Chair because it's the easiest. Okay, so whenever you guys were doing chairs, you learned, wedges are up and dashes are down, right? And remember, axial and equatorial have nothing to do with wedges and dashes. Okay, uh, wedges and dashes has to do with the direction of the substituent. If is it pointing up, is it pointing down? You can have an axial pointing up and an axial pointing down. You can have an equatorial pointing up and you can have an equatorial pointing down. Okay, so let's say my leaving group looks like this, and I know it's SN2, so I'm going to draw that. And let's just label this as LG. Okay, so if it's axial or equatorial pointing down, I'm going to put axial pointing up for my nucleophile. Whenever, like if I know for sure it's SN2. Okay, now let's look at Fischer projection. Okay, so I don't care where everything else is. Let's just go with this LG. All I have to do is flip it to the opposite side. That's all. Okay, and obviously with each of these, a very foolproof but a little bit time-consuming way is to check chirality. Okay, if chirality of that single carbon is flipped, then it's going to be that means you did good, because sometimes you might not have wedges or dashes, but you might have a line. Okay, and whenever you have a line, you still have to flip the stereochemistry, and you can do that by checking chirality. And then lastly, which I think is the harder ones, is Newman projections. Hydrogen here, methyl. I have my leaving group here, hydrogen, methyl. Okay. What's this? Okay. So one way Well, there's several ways to do this. Okay, one way is to change it to a line angle, find your wedges and dashes, and then flip everything. Okay. The other way is to rotate the carbon. So if it's on a wedge, rotate to the other side. If it's on a dash, rotate to the other side. Now, if it's on a line, I believe you can just flip it and add your nucleophile. Okay, so notice how my lines changed. So everything's the exact same, but now it's completely flipped. Okay. All right. So this is a very key, important aspect of doing. So you will see Newman, Fischer, and Scher on your exam. Okay, either one of them, all of them, maybe none of them. You know, if you see none of them, don't come for me. Okay, I'm just making sure you guys are prepared. Okay, so these problems I'm choosing specifically because these are very specific problems that you might not see in a regular, practice quiz, practice exam. Okay, and I believe the rest of the normal problems you should be able to figure out using everything I taught you. So the next weird one is something that has two bromines. That is not a B, that's a B. What is wrong with my B's? Okay, anyways, let's say you have Ki and you have two bromines. Okay, so Ki is a strong base. So K means it's a strong nucleophile or base, and then so this is a strong base. Okay. So I have two bromines, right? So which one do I pick? Really, it doesn't matter. All you need to know is that there is a anticoplanar hydrogen, or actually there is no anticoplanar hydrogen. But whenever you see this might not be a strong base. I do know that it's elimination. So whenever you see two bromines and a Ki, think of elimination. And then you're going to form a double bond between these two. Okay? That should be the end result. I kind of forgot how the mechanism works. I believe like one of them leaves, and then this comes in and forms the double bond. I think that's kind of how it works, but I'm not too sure. Just know that this is a weird one and you kind of have to remember it. Another one is something called Solvolysis. Okay, now this one is very, very high yield, which means that it will always be on your quiz or exam, most likely. Okay, which is AgNO3 and methanol. Okay, so the definition of solvolysis is when nucleophile is also your solvent. Okay, or solvent is also your nucleophile. Okay, in this case, my methyl is our solvent, and it's also going to be the nucleophile. Okay, so this is both nucleophile and my solvent. Okay, So if this is my nucleophile, is it strong or weak? I see my H, so it has to be a weak nucleophile. So weak N, so that means I'm going to be thinking of SN1. So yeah, methanol is going to be weak nucleophile, weak base, so it can be SN1 or E1. But when in doubt, I would personally put SN1 over E1 unless you are using H2SO4. Hydrosulfuric acid is almost always going to be elimination 1. Okay, it's going to be E1. But for now, let's finish this problem out. So if I know it's SN1, I have a secondary carbocation. I see a tertiary hydride shift that I can do, so I'm going to do that. And I'm going to attach my OCH3 just like that. Okay, so that should be your final answer. It's going to be SN1. Number 9, it's not really a question, but if you see H2SO4, do E1. Okay? Alright, so we're actually going to stop right there. I'll scroll back if I need to. There's 7, 8, 9. There's number 6. There's 3 and 4. And there's 1 and 2. And then there's all the ranking questions. Okay? Alright, so those are lots of practice problems we went through, lots of unique examples, and I kind of showed you guys my thought process on how to label. I hope you guys are understanding everything I'm saying. I hope it's being very clear. If it's not, obviously please don't hesitate to reach out to me. The best way is to come in person into Peer Tutoring Lab. We're in the basement of the library. Monday through Thursday, 10 to 6:30. Friday is 10 to 4. Saturday, 12 to 4. Saturday is online. I work Monday, 3:30 to 6:30, and Wednesday, 2:30 to 5:30. So if you guys want to come see me, those are my times. But please reach out to all the tutors. They're all great, and maybe some of them know even better than me. All right, I will see you guys next week. I know that next week is the exam, so there is an exam review or like a weekly review, and there is also an exam review that should be posted on our YouTube page. Usually these weekly reviews are posted a couple of hours after, so I know it's the day of your exam, but please still review that video. But if not a lot of people, if I don't have much to say, I might not post the video. So yeah. Anyways, I'll see you guys next week, and if I don't, good luck on your exam.